I've made the title here as low latency surveillance using neuromorphic vision sensors. And I think you can understand everything except neuromorphic vision, right? But before we jump into that, let's look at how things are done now these days for IoT especially and for ITS. So we have a bunch of sensors which are always on, and we are sensing passively. We're not sensing actively. For example, if you have a camera, which we call as an active pixel sensor, but in fact it's actually sensing at intervals, and it's capturing an image regardless of what's happening in the scene. For example, if there's no bike or a car, I'm still capturing an image, right? So there is a lot of redundancy in the way we are with the sensors that are currently being employed. And these are the standard RGB cameras in your phones, and in surveillance cameras that you see in the street, and that the ones that you employ in your home for security. So whenever we capture an image, we need to communicate that result to the cloud and to detect objects or make some decisions. Or we have an edge processing device which has to still compute and say that, hey, there are no objects in the scene. So standard IoT with standard vision sensors consumes high power. So you have to always make sure the images that you're capturing are being processed. So, and when you talk about IoT within power constraint scenarios, say, for example, sensor that is being powered by a battery instead of being powered by the grid, the lifetime of these devices is being limited by this constant sampling, right? So it's very difficult to deploy these systems in unattended areas, especially remote areas. So how can this scenario be differently addressed? So this is the main motivation, right? Sensors are not intelligent per se. They are just capturing images regardless of what is happening in the scene. So within ICNS, International Center for Neuromorphic Systems, we have three main research streams. One is actually building these neuromorphic sensors. The other is algorithms and how to actually compute with these sensors. And the third one is actually building neuromorphic chips. All right. By neuromorphic chips, I mean, you have an Intel chip in your laptop or in your PC, which computes serially, right? Neuromorphic chips compute parallelly, much like our brain, much like our nervous system. So when we talk about biologically inspired sensors, that's what I mean by neuromorphic. We are mimicking the biological principles. So we could mimic the principles that are within the eye, for example. Then you can have a neuromorphic vision camera. We can mimic olfaction, our smell. Then we can have a neuromorphic olfaction sensor. We can mimic the ear, which we call the neuromorphic cochlea. And we can also mimic the tactile, the touch part of our sensory system, and we can have neuromorphic tactile systems. And when we put everything together, you have a mechanical system which is neuromorphic. Right? So let's first see what a neuromorphic vision sensor looks like. So this is going to be a quick video, but I hope you can take a look at it. So we have a conventional camera on the top left, and we have a simulated event-based sensor or a neuromorphic sensor in the bottom. You can see that the conventional camera captures RGB images at fixed intervals, 30 frames per second in this case. And the neuromorphic sensor captures changes only when it is triggered by the moving object. Fantastic. In this case, it could be this cloud, it could be the rocket that is moving up, or this stampede that is happening due to this animals coming, right? So on the right, I'd like to show you this graph. Here, the yellow graph corresponds to the conventional camera. Within a few seconds, you're already in the range of gigabytes of data. right? Because this is HD, even more than HD resolution. But when it comes to the event-based sensor, which is in green, we're only capturing the changes, which means I don't know what the background is. I don't care what the background is. I only care about what is moving. And that's how our eyes work. All right. Our eyes are actually sensing changes all the time. They're not actually registering intensity at a particular level. They're only sensing changes. And it magically gets represented as what I'm seeing as the image of Chandra or the image of, an empty chair here for P. Ramakrishna. So all these things are happening magically inside our brains, but the very fundamental hardware with our eyes is they only sense changes. All right. So that's what these cameras try to mimic. So you would see something like a binary image output out from the cameras. You don't capture images, you don't capture intensity, you don't see nice pictures with these cameras. You only see temporal changes being captured. And a similar philosophy is also employed for the ear. So ear also has a similar philosophy of recording the changes in frequency rather than registering absolute frequency changes. And those changes in the frequency get mapped to the words that you're listening. So there are all these hair cells inside our ear that sense the vibrations, the changes. And you can have a cochlea, a silicon cochlea, or a neuromorphic cochlea that does exactly that. All right, so with these sensors, how can we move towards AI systems or neuromorphic object detection systems or classification systems? So that is the main theme of today's talk. How can we make use of neuromorphic vision sensors and deploy them in intelligent transportation system scenarios, especially for traffic surveillance? So again, I'm going to reiterate. I'm going to reiterate it a few times until one of you asks a question. All right. RGB sensor is a synchronous pixel sampling. It consumes high power. And if you have noticed, pointing your camera at the sun, the surrounding objects will become a bit dark. You won't be able to see the sun as well as the other objects because the pixels get saturated. So it has a very low dynamic range. But when we talk about the neuromorphic vision sensors or the NVS, each pixel is an intelligent unit. It can communicate its change without relying on absolute intensity. As whenever there's an intensity change, it gets triggered. So the output from these cameras are the XY location, where the pixel spiked, and what was the polarity of the spike, whether the spike was triggered due to an increase in intensity or a decrease in intensity, and the timestamp, at what time duration that this spike occurred. That's what I've mentioned here as this XYPT. That's your output from each pixel. So it's very different, right? It's not anything that we are used to. If you have a nice image, you can do image processing. If you have a nice edge map, then you can see, oh, these are all the events. But you don't have that kind of output with NVS systems, neuromorphic vision sensors. So again, I'm going to illustrate the difference between the neuromorphic vision sensor and the conventional sensor. This time with a more simpler example, so you can understand what's happening. Okay, so imagine this rotating disc is being viewed by a standard camera, top, and a neuromorphic vision sensor, bottom. As the disc rotates, this black dot rotates, you see temporal changes being registered by the neuromorphic vision sensor. Whereas a normal camera would capture, normal images, intensity images at fixed time intervals, right? So what happens when the dot stops moving? you get no events from the NVS, whereas the standard camera is still capturing images at fixed time intervals. So this is redundant, right? So what happens when the disk is moving fast? You get motion blur with normal cameras. That's what happens when you try to take a selfie and then your wife hits your hand. You get motion blur. So these are intrinsic problems with the way conventional vision sensors operate. And neuromorphic vision sensors, when the object starts moving fast, you get events faster. That's the only difference. So there's no paradigm of motion blur here. We are only registering changes over time. And in some cases, this is also called as temporal difference, right? These pixels are sensing the temporal difference. So I'm going to stop here and ask if anybody has any questions about the sensor itself.
Dear participants, we have not only from civil engineering and transportation engineering professors, we also have computer science and information technology, electronics, communication. So you can participate now. This is the time.
Sir, good afternoon. A very simple question. Don't mind or laugh. X-axis is fine. What is Y-axis, sir?
So, okay, look, the Y-axis is Y, right? XY is your image grid, your field of view, and the third axis is your time. So the native space of both these cameras are the same, right? There's no difference in terms of the native space of both these cameras. It's how they are sensing. In fact, you can take a normal camera, and when you do a frame difference, you will see something like the output of an event camera. But that's saying I will now change the principle of a conventional vision sensor without actually changing the hardware. But now that temporal difference is happening at the hardware level. Imagine your images are being background subtracted, right? That's what you get from neuromorphic vision sensors. So,
Dr. Bharath, sorry. Yeah, please go ahead.
So this is XY, and your third axis is time. Any questions, sir?
Dr. Bharath, we are, I mean, we in the sense, common public, from point of view, we know like something exists like motion sensors, motion sensor camera, security systems. This is completely different, right? It is not the way how that works. There is no neuro element there.
Yeah, I mean, this is not making use of a motion detector per se. Each pixel is receiving photons.
Yes, yeah.
And
so that's
there are like hardware thresholds. And when that hardware threshold is hit, that pixel spikes.
So that is where the neuro part comes, I guess, right? So
exactly. So that's a principle within our eyes, right? Whenever, for example, if you're focusing on a task and something moves in the background, your attention gets shifted to there, because the temporal difference is happening within your eyes. That's the crudest example I can give you of how an eye would do temporal difference. But when you actually see the biology of it, the neuroscience of it, these cells actually capture temporal changes.
Wonderful, sir. Wonderful. Please continue. Wonderful.
Sir. Hello, sir.
Yes, please.
Sir, we have seen that this neurosynchronous neuromorphic sensors, they capture only the events, and in some cases there are chances that the events might reoccur. Is there any possibility that these would delete those particular events?
Okay, so another thing that you need to notice is, do you see that these events are very close in time, right? So the time resolution of these cameras is in the order of microseconds.
I see.
So events get triggered at the level of microseconds. So it doesn't mean that it will get swiped away by another event, because it's already triggered.
Yes, sir. Thank you, sir.
Great question. Good question. Thank you.
Very glad, very glad. So, participants, sir said initially,
So,
but yes, please continue. Yes, that's what I was thinking. Please carry on.
good afternoon, sir. This is Swarnamukhi from Bangalore. I have a small question here. The
Yep.
video that sir played, it was
No, you can just call me Bharath. Don't say sir.
okay, 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 Mr. Bharat.
You're probably elder to me, I think.
Okay. Yeah, of course. Mr. Bharat, the video that you showed, it focused on one single object changes. Is it like this NVS is possible to capture the multi-object changes? And in that case,
Sure.
how
I mean,
far it is
it's
related?
not related to one single object. You should now think in terms of each pixel is like a different sensing unit. Like if you have a 240 by 180 neuromorphic vision sensor, each pixel can trigger regardless of what's happening in the other places. So it's not related to one object or anything like that. It's not dependent on the scene. The pixel itself will get triggered. For example, if I have a handheld event camera and I shake it, right? You will see all the edge-like patterns. Wherever there are changes, the gradients that happen in the scene, the events will get triggered. Mostly they will be at the edges because that's where the change in information is. For example, I'll give you a simple example. You can see Chandra here and his background is white, right? The intersection between his background and his face is where the gradient changes. So mostly the events will get triggered at those locations. And of course, his beard and his face and his spectacles, you can see all that. It's not related to objects per se. It's related to the temporal gradients in the scene. But good question. Good question. It takes. I know it takes some time to get used to this concept. I had a colleague.
Sorry, someone is asking. Who may I know who is this? And they wants Dr. Bharath.
Yes, sir. Hello.
Yes, you can ask the question. Dr. Bharath is waiting for you.
Yes, sir. I'm Rameshwar Bhattacharya.
Rameshwar, yes.
Sir, I'm just a query related to this topic. That when we see the broadcast of a cricket match, then in case of LBW, we can see that the ball tracking, which help us to know that the ball was going to touch the wicket or not. So my question is that is this ball tracking images are captured by this type of event camera?
India being a country with such cricketing background, I'm not surprised that this question came up.
Yes, that's an interesting question. Yeah.
So you have to you have to always think in terms of what is also moving alongside it. This is not a ball tracking system.
Okay.
Right. So you have to think in terms of the sensor itself is different. It's not just depending on. This is not tracking the ball, by the way. If something else was moving in the scene, it will also show up as the output of the event camera.
Okay, sir.
I think I accept. I think I agree with Dr. Bharath because once he goes, this is basically he is giving the definition. Once he goes later to the application, I think most of your doubts will be cleared automatically.
Correct. But good. I mean, let it keep flowing. It's good.
Yes. Sir was asking about more on the concept level. If we have any questions or anything, so that he can go proceed with the other things. Thank you, Rameshwar. Thank you.
Mr. Bharath, I have a question.
Your name, please. I'm noting in the names.
Yeah,
also.
Sanjay.
Could you please?
Sanjay Sharma.
Sanjay. Okay.
Yes.
Thank you.
Actually, what is the neuromorphic basically?
It's bio-inspired.
Neuromorphic means?
Bio-inspired.
Bio-inspired.
Yeah.
Bio-inspired. And what is the neuromorphic chips made of?
Well, they're made of silicon, but just that they function very differently compared to normal chips.
No.
They work in terms. Just think about your brain, right? Your brain does not wait for you to think one particular thought and then the other thought appears. Everything happens simultaneously, and then you have this moment of insight or moment of understanding. That's how these chips try to classify or detect. They try to process all the data simultaneously and then give you some meaningful output.
Sanjay sir,
Okay,
Sanjay
okay.
sir,
It is, yes.
Sanjay sir, Dr. Bharath mentioned initially one word he mentioned. It's like a humongous parallel processing. He mentioned about the parallel processing. It's not one thing sensing. A set of many parallel things are sitting at the same sensing at the same time. He mentioned initially about that parallelism in this particular kind of thing, and also he compared how our brain works. So that's where I think he gave that note.
Okay, sir. Okay, sir. I got a point. Okay.
Thank you.
Thank you,
That's
sir.
what's up.
Yeah. Is there any questions, guys? Or else Dr. Bharat can proceed. I think you can proceed, Dr. Bharat.
So no questions with the sensors. So I am assuming that most of you at least 10% understand what the sensor does. All right. So you will understand more as things go.
We are grasping slowly. Yeah.
So we are trying to combine the neuromorphic sensors and algorithms for embedded ITS applications.
Okay.
Right. So there are 4 different parts to my presentation, and I will go through this neuromorphic system pipeline methodically, and how we actually started and how we evolved and how we were and where we are now. All right. So we have this vision sensor, neuromorphic vision sensor, and we can have this neuromorphic chip, which can do at the edge, right? So this is the simple pipeline. It's just that we are now replacing the sensor with the neuromorphic sensor and the typical edge computing stuff that you have with neuromorphic chips, right? So everything will become even lower power. That's the idea. So the sensor will consume about milliwatts compared to, say, a few watts from the usual vision sensor. And your neuromorphic chip will be in the order of, again, milliwatts compared to, say, hundreds of watts when you're talking about GPUs and when you're talking about TPUs, right? Maybe a few watts. So you can have about 10x reduction in power when we are talking about neuromorphic systems. Yeah.
Yes, somebody is entertaining them. Wow. So now they can see the application, they can understand better. Yeah.
Okay. Can you hear me now?
Yes.
So this is a typical neuromorphic system pipeline, and this is a very short demo of how our system output would look like. So you can see that you're not actually seeing the background. You're seeing something in the form of a bus. You're seeing something in the form of a car. And now you need to be able to classify that that's a car and this is a human. You see, the human is almost just a few pixels moving around, right? That's what you see from the output of the camera. It's very different. And only for your reference that we have this RGB camera output. We are not actually making use of the RGB camera output at all. This is just for your reference. What does the scene look like? What is moving in the scene? So you see a bus coming, or you have a truck coming. Okay, I should be able to name it as a truck. And this whole thing is an embedded system, from the sensor, to the tracker, to the detector, to the classifier. Everything is this embedded system, and we'll talk about this today. So this is what we are focusing on.
Fantastic. Okay, everything is embedded there.
Right. So this is what the block diagram looks like. So you have the output of the DVS camera or the NVS camera. DVS is just another name for neuromorphic vision sensor. DVS stands for dynamic vision sensor, right? But it's still the same thing. So you have the output of the event camera. You have to do noise filtering. And why do you see noise? Because, at the hardware level, you have a lot of this wrong triggers at the hardware level due to the mismatch during the fabrication process of the camera. So you have all these pixels that are triggering for no reason, right? So you need to do noise filtering, and you need to implement the tracker, And then once the tracker is implemented on the FPGA, then you can actually push it to the neuromorphic processor, which can split the trackers, which can do time division multiplexing, and actually do the classification, right? Then you get this nice result. See, that's a car, that's a bus. So it's a low power, end to end, right? From one end to another, it's neuromorphic. It's a hybrid neuromorphic because we are actually touching upon something that also relies on, time multiplexing, right? That's why it's hybrid, because you are now accumulating events within a small amount of time. So in a sense, you're actually creating a frame out of the event camera. All right. So you say, for example, the first 33 milliseconds, I want to aggregate all the events into a single binary image. You can do that. So it's a hybrid framework. The reason why we are doing that is actually counterintuitive to many neuromorphic vision researchers. They don't like the idea of creating an image from a neuromorphic vision sensor, to be very honest with you. All right?
I see. Dr. Bharath, it is very interesting to know about that. I have to, because I was waiting for right moment to interrupt you. When you say about, is this like in astrophotography, we use something called stacked images. We collect photons looking into a galaxy or a nebula, and we collect the light. From one frame, you can't do anything. It may be one or two photons. After we collect and put them together, we see a picture there.
That's a good analogy.
Something like a good analogy. Okay, thank you.
That's a good analogy. But here, we are talking about temporal events. Events
which
are triggered
Okay.
due to the changes in the scene.
Fantastic, right? Because these are all moving, guys.
These are all moving objects, and you get triggered. You get events as and when they are triggered. But now we are saying, right, you don't have to process as and when they are being triggered. We will wait for some time, say for example 33 milliseconds, and then we will get a frame like this, a nice frame output, and then you can process this frame output.
I see.
Typically people don't like this. I will be very honest with you, because neuromorphic sensors and aggregating frames don't go hand in hand. Because if the scene is, if the objects are moving fast, right, then if your aggregation interval is fixed, say 10 milliseconds, depending on the motion of the objects, the aggregation could look blurred, or it could be nothing. There could be nothing in the event aggregation. So this is not a typical neuromorphic pipeline. So that's why we call it hybrid neuromorphic, just to satisfy this purist neuromorphic people. Because if we call this neuromorphic, then they will say, no, this is not neuromorphic. Then we have to say it's hybrid neuromorphic, right? So let me jump into data collection first, right? Then you will be interested to see how what we did and how we actually implemented the noise filtering and tracking and so on. So let's start with the basics. You have a project. You want to implement a neuromorphic vision system for a traffic application. What do? You go to different places in your campus, or you go to different places in your city, and you want to collect data. You want to see how the tracker can be implemented. You want to see how the classification output is. Because initially, to start with, you have no idea, right? You don't know where the things are. You don't know what it is, right? That's the approach that we are taking. This what where approach. Where is something that gets triggered, and what is it? This is the pipeline that we want to implement. This what where pipeline. So let's start with dataset collection and annotation. So we chose 3 locations inside our campus. Chandra will be familiar with some of these locations inside our campus.
Wow, I start missing NUS now. Okay. Very nice. It's a beautiful campus.
We chose 6 different objects to classify: a car, a van, people, bikes, trucks, buses. This is something that we chose because these are the commonly occurring objects, right? So you need to do data collection now, and you also have to think about what lens to use. And when you talk about neuromorphic vision sensors and lenses, they are not any different. You can use a typical lens that you use for your standard camera. They're not any different. The pixel is not doing anything different except detecting changes. It still needs photons. It still needs light, right? So the lens is the same. So we have to go, intern students have to go and collect data. Of course, we as researchers sit inside our cubicles and say, hey, you go and collect data, right? So our intern students will go and collect data for 1 hour, 1.5 hours. They sit there with their mobile phones playing games while they're collecting data. And when we initially started, how do we annotate this data, right? No one has actually done this before. There's no tool out there to just record this data and start annotating it. So we have to build our own tools to annotate the data. So this is the Annotate app that we built for loading this data into our system and creating different tracks and labeling these tracks as cars, and then try to be able to interpolate between two boxes so that you don't have to click through all these things. So what you have to essentially do is choose 2 points where the object is and where the object ended, and the system will interpolate between these 2 boxes. And you can check the output by playing it back, and maybe you can redraw the point, delete some points, add endpoints, and so on. I'll go through this iterations. But before that, can we actually take a step back and say, do we need all this manual efforts? Like, do people really have to click through points and annotate data, right? Can we actually automate this process? So you can actually automate this process by having an RGB sensor, which is recording data simultaneously along with this Davis camera. Davis stands for Dynamic and Active Vision Sensor, DVS, right? It's the same thing. It's a neuromorphic camera. Z is just a normal vision sensor. So if we can run some deep learning algorithm which can detect a car, and if we have calibration between these 2 cameras, then from the bounding box from the car, you can actually go to the bounding box in your event stream. So this is one way of annotating automatically. But how reliable is this, right? That's the question that we were faced with. Can we record a simple scene like this and start annotating based on some deep learning output? The answer to that is much more complicated, right? For the same frame, just a slight difference. You can see the car is being detected and then the car is not being detected. So it's a very unreliable source for annotating data automatically. But if you take a look at the output of the vision sensor itself, the neuromorphic vision sensor itself, I would think that's a much cleaner data for tracking compared to this RGB output.
Yes.
Right?
Yes.
You are just seeing the cars coming and going. For example, here you see this person being detected. You see this car. Okay, can I actually make use of this output to automate this process and not make use of an RGB sensor to begin with? Because there are many problems with the RGB sensor. We criticized it, and then now we are saying, can we make use of an RGB sensor to annotate our events? Right? So that's not a good approach. So what we chose is a semi-automatic method, just making use of the event domain to annotate data. And this is what the system actually looks like. Okay. You can load the data, and when an object enters the field of view, you can put a bounding box, and you can make use of a robust tracker, which we developed to automatically annotate.
I see.
And you can, of course, correct these errors. If you think the automatic annotation is not good, you can again add points and then redraw the point, delete the point, and name the car. Okay, that's a car. Done. So this is much simpler compared to making use of simultaneously recorded RGB data, relying on deep learning, parsing that output and passing it to the event domain. So this is the annotation app that we developed. This is something yet to be published. And in fact, what we have done is to compare the RGB output and the event camera output is something that everybody is interested in. Everybody is saying, okay, for the same application, how does the output of the RGB camera perform? This is something everybody is interested in. So with this ground truth, and if we have simultaneous RGB recording, we can actually transpose these ground truth in the event domain to the RGB domain. And then still make use of some deep learning and say, hey, look, that's how it performs. We should not make use of the RGB and go to the event domain. Go from the event domain, which is sparse and which is easy to track and annotate, and go to the RGB domain using calibration.
Okay.
So this is something still ongoing work. I just wrote the introduction to that paper. It's targeting the computer vision community and actually encouraging them to make use of neuromorphic vision sensors and simultaneously recorded RGB data if they have it, to compare for a particular output and a particular application. How do these two sensors perform? No one has released a tool for comparing these two sensors in a very rigorous way. So that tool can be very helpful to the community.
Dr. Bharath, I think that's amazing. I'm so happy that you have that human element inside there. It's not completely artificial, so that gives us a validation for traffic transport engineers that yes, everything will be all right. Somebody is out there.
So yeah, let's talk about algorithms, right? We haven't annotated the data. We have some ground truth. We know that some data belongs to car, some data belongs to truck. Let's see how we go about doing noise filtering. So a typical idea within noise filtering is, if a neighboring event doesn't occur within a short time period, most likely that's noise, that's random noise. So we check for the neighbors within a particular, let's say an event gets triggered at 10,2, that's the pixel location at this particular time instant. We check whether there were neighboring events. And if there were no neighboring events, then we just throw that event away, right? It means it was just hardware noise. So this was again implemented in FPGA by a very clever Italian guy called Luca and another guy called Garrick. So there's a big team behind this. I'm speaking about a project which happened during the last 4 years. So it's a big project. Many people have been involved in this. I'm not the only one, right? So you can do noise filtering, very simple. You just use a typical threshold of 50 milliseconds and say, within the last 50 milliseconds, if there were no neighbor around that event, then that event is thrown away. That's it. Very simple. Simple logic. And how do you actually go about the where pathway? Right? Where do you look at? So you can create very simple region proposals by making use of the sparse output from these cameras. Let's say you come across this particular scene. You do a one-dimensional histogram along the X, basically saying, here are all the events at in this X location. These are all the events, and I count how many along those X locations. So you can create a X histogram. Similarly, you can create a Y histogram, and the intersection between these histograms will likely be locations, candidate locations where objects are. All right, so very simple. This we call as hist RP. RP is region proposal, where pathway. And then you can also go about doing your typical connected component analysis, where you go through each pixel and say, okay, these are all the connected components, and you label these into different regions and say, hey, look, these are all the different region proposals. So these are all very simple image processing operations. Like they date like 40 years back, but we can make use of them for a new domain. You see, that's the novelty, right? You don't have to reinvent the wheel entirely. You can still make use of old tools that you have. And that's why this term hybrid neuromorphic is very useful, because you still have an image now that was accumulated during the last, say, 33 milliseconds or 66 milliseconds. I will talk about more about the time accumulation later on. So this is how the region proposal looks like, right? You see all these cars coming and going, and the CCL, the connected component RP, will be less fragmented. Sorry, it will be more fragmented, but it will be more compact. Whereas the histogram RP will be a bit elongated or will be a bit larger, depending on what object occupies the top of it or the bottom of it. Because let's say you have a smaller object, behind the bigger object. Like in this case, you have this very small object. Can you see my cursor? Yes?
Yes.
Yeah, so you have this very small object. Maybe I can do a pointer. Yeah, I can do a pointer, right? Yeah. So you have this very small object, and with the histogram RP, you get this big bounding box. That's not good. But with the CCL RP, you get a smaller bounding box. Sometimes it will get fragmented. That's the trade-off between hist RP and CCL RP. Okay, so object tracking. Again, very simple ideas. Nothing out of the box. Nothing too complicated that you can't understand. Simple idea. For example, if you have an RP at this particular time instant, and another RP appears at the next time instant, if they are close enough, then we say, okay, that's a track. A very simple overlap based tracker. All right. If two tracks lie close to each other, then just combine them. As simple as that. Now let's take a look at how the tracker performs in software. This is C++. So you can see that if there's an RP that was happening very close in time, then we just label it as the same track. Quite simple, right? But then, when two objects come together, then they become a bigger RP. So we had to make use of occlusions handling scenario. So there we had some heuristics to say, if two RPs are crossing each other, then we just maintain their state until they cross, and then we have this heuristic for tracking again be applied. We don't make use of the heuristic while they are crossing, because we know that they are crossing. We know the flow of the RPs, right? This RP is coming here, that RP is coming here. So the flow is happening this way. So you don't do the tracking during this time. Just maintain the bounding boxes. And as they separate, then you just give the bounding boxes to them. It's a very simple occlusion handling scenario.
Dr. Bharath, these algorithms, they develop as you get these problems, you are introducing new algorithms. That's how it goes, right?
Correct. So you don't know what to develop first. You look at the data and you see how to keep modifying these algorithms. There are several iterations behind it.
Okay. Fantastic.
So this is the FPGA tracking. Okay. So this is the FPGA implementation of that very same thing. The reason why we are going for FPGA implementation is then you can port it to an ASIC. Once you develop an FPGA, which is programmable, then you come up with your electronic design, and then you can have an ASIC for that. So it can be even lower power. FPGA is just an intermediate step for us to develop something. All right, so that's the tracker. So how do you evaluate these things? And right, so we have the ground truth from the annotation. Now we can actually make use of very simple precision recall and intersection over union, which is basically saying if the ground truth overlaps with the track more than 50%, then I count that as a good track. As simple as that.
Okay.
So this is an evaluation. Green is the ground truth, red is our track, right? And then once you give this type of evaluation, people will ask you, where is the comparison to deep learning, right? So you have to now think about how to actually compare your work to existing frameworks. You can't just propose something and say that this is my work and this is what I know. You can't do that. You have to always compare it to something which is existing and what people accept as SOTA, state of the art. So this is something called Siamese networks, which work on RGB data. So you give a bounding box, it can make use of deep learning frameworks to do the tracking. That's all we need to know. I don't really care about how it does and exactly blah, blah, blah. I just need to care about, what it does, whether it is state of the art. So when you compare a Siamese neural network to a traditional CNN, a traditional CNN does not have an online learning component. A Siamese network has an online learning component. That's why when you're able to initialize that bounding box, that network is able to learn based on that bounding box and just keep learning and track the object.
Nice.
That's a simple explanation I can give you for Siamese network. It's basically a similarity score between your previous bounding box and your predicted bounding box. And if that's close, and then you say that's a good track. So we initialize Siam mask with the ground truth labels that we annotated with, right? So we give it a fair trial. Of course, you have to give it a fair trial. You have to give it the bounding box that we can best give, the ground truth. You don't give the RP to the Siamese network. That will be detrimental to it. So this is the latest result that we have. So F1 score is the harmonic mean between precision and recall. IOU is the intersection over union. Like if it's 50%, that's 0.5. If it's 40% overlap, that's 0.4, right? So as you increase that threshold, of course, your F1 score will decrease. So you can see that the red curve, which is us, EBI naught. EBI naught is a fancy term that we came up for the system, right? It stands for event-based binary image neural network overlap track, right? So it has all these components tied together. And you can see that of course, we can't be deep learning, but we are very close. And in fact, the green line is the event-based mean shift tracker developed by people from Zurich. And this works purely with the events. So when we compare the green and the red, we are doing much better. And when we compare the red to the deep learning models, yeah, I mean, we are not that bad, right? And especially when you consider higher IOUs, in fact, we are beating the deep learning systems. And that's I would say, a marginally good result. So I have now covered noise filtering and tracking. Now let's move to the neuromorphic processor itself, right? And I hope you all will be interested to know True North. So True North is a neuromorphic chip developed by IBM. They also developed the framework to train these chips. So we just make use of these frameworks to train and deploy this spiking neural network architecture on this neuromorphic chip. So neuromorphic chips will not process like a second generation neural network, like an artificial neural network or a convolutional neural network. They will make use of spiking domain, the third generation neural networks. So they have a framework called EDEN, energy efficient deep network pipeline, which we make use of for training spiking CNNs. So we give the input, we give the output labels, and then EDEN can give us a neural network that can be deployed on True North. So True North is essentially having 4096 cores, and inside each core there are 128 neurons. How these neurons have to be connected is what EDEN does, and it does at the back end for us. We don't have to worry about it. IBM has to worry about it, right? But there are some things that we need to decide. Do we have to do noise filtering? Does it help or hurt? How much data should be contained in a frame? What size should we give to the True North model? So these are questions that we need to now still think about. So this is a test that we ran based on different filtering size, different filtering time intervals, and different pixels that we chose for input to the True North. And what we actually saw was the more filtering that we did, the humans disappeared from the event stream totally. So this was actually hurting the human class. And the largest sizes that we had for feeding to True North, that was giving us better results. For example, if you compare the 30 cross 30 to the 42 cross 42, it has a marginally higher accuracy. And what we chose at the end was we will choose a 42 cross 42 region around each object with no filtering because it hurts the human class, and a 66 millisecond time period for aggregating the frames. So these are all trade-offs that we come up with when we are developing a system. a practical system especially, right? So this is results on the ground truth data. And what you're seeing is the overall accuracy as 83% when you train and test on the ground truth data. Augmented is just, you're introducing artificial flips, rotations to the deep learning model before you train it on true north. So it can give a marginal improvement again, 85.1 compared to 83.3. But the real question here is, should you actually make use of ground truth annotation as such for deployment? And the answer is you should not, because the FPGA tracker will be very different compared to the ground truth. So if you train your system on ground truth and deploy it, it's not going to be optimal. And that I think is the key takeaway from all this, right? I can show you n number of things, but the key takeaway is, if you have ground truth information and you want to deploy that, you should also see what your system is doing, your pre-processing is. And if your pre-processing is different to the ground truth, now you need to think about alternate ways of training and testing. But the tracker output from your FPGA does not have any ground truth labels, right? So you need to infer the labels from the ground truth. So you can run through the FPGA tracker and get the track output and compare it to the ground truth, and then you can now label the FPGA track output. And that is what you should be making use of for deployment. So you should make use of the tracker output for training rather than the ground truth for training. So because the ground truth is very perfect, but the tracker is not perfect. And True North is actually working on the tracker output, not the ground truth that you had. So that's the key takeaway.
Dr. Bharath, one second. I will just interfere here. Dear participants, you can see that the entire efforts experts like Dr. Bharath are doing are to reduce our pain in collecting data about vehicles. You can actually have a drink or something. I mean, like, it's already late night for you. We are sacrificing your comfort for us. Maybe you can have a snack or something for 5 minutes. We will wait. Yeah.
No, it's good. I think I'm reaching almost 3/4 of my presentation. So it's okay. It's good.
Thank you very much. Please go ahead. Please go ahead. Thank you.
So that's how you label. Okay, just recapping that. So you have to infer the labels from your track output. And because the track output is what is being used by your classifier, right? It's not actually making use of perfect bounding boxes around your object. Sometimes it can be fragmented. So these labels have to be inferred from the ground truth. So labeling ground truth is not useless. It's useful, of course, but you have to use it in an intelligent way. So this is our training testing distribution of our FPGA track and our ground truth track. We don't need to look at too much of this, but the key result here is, okay, now let's focus here. I mean, this is very important. True north accuracy using ground truth training. So meaning you make use of perfect bounding boxes for training and testing your true north model. Of course, the ground truth test will be good, 83%, like we saw before. But the FPGA tracks, which are fragmented and sometimes not perfect, will only get an accuracy of 48.7. So when you actually deploy the system trained using perfect ground truth bounding boxes around the object, you will only get 48.7% accuracy. All right. Whereas if you train using the FPGA track outputs and the labels that were inferred from the ground truth, you can push the accuracy to about 70-ish, because now the partial object that was labeled as a bus can be correctly labeled as a bus by the True North model. Previously, you were training on the perfect bus and testing on the fragmented output. Now the fragmented output has already been labeled based on the inference from the ground truth. And if you deploy this system, you can get about 70-ish accuracy. And the interesting thing that you note here is, if you test on the ground truth, of course, you will get much lower accuracy, right? 63% overall balanced. So that, I think, is the key takeaway. Whenever you are deploying a system, think about what the pre-processing is and suit your needs according to that. So even this 70% accuracy is actually about 81% accuracy. The reason why I say that is, when ground truth annotations are created, humans generally don't tend to label the object just when it enters. They will wait for it to maybe enter 3/4 and then they will say, okay, that's a bus. So we have this mismatch between the ground truth and the track output itself. So the ground truth itself is not perfect, right? Because no human can label this as a bus. I don't know whether this is a bus or a truck. Until it enters, then I say, okay, that's a bus. So let's look at the demo of the system, which I showed you previously. Very short demo, but this one will be a bit longer. And also HD, right? Of course, the system is not perfect. Sometimes it will flutter between different objects. Like, for example, when you saw the truck, sometimes it was classified as a bus. But when you take the majority voting, when the object entered and when the object exited, you can say that the bus was there 90% of the time. Then you know, okay, that was a bus. Maybe 10% it was misclassified. Doesn't matter. So you don't have to make use of individual outputs to make an informed decision. You can make use of the full track output to say, hey, that was a bus. Hey, that's a human. And this is where it was. All right. So that's the demo. And let's take a look at briefly. I didn't do this work. A lot of people did this work. A lot of guys very proficient with FPGA and a lot of hardware. They did this work, and I just oversaw most of it. So they did all the comps, they did the integration with TrueNorth, the integration with the Davis camera. Davis, stands for the neuromorphic vision sensor. So they did all this hardware design, and eventually the power consumption was about 2 watts. But that's because we are making use of an FPGA, and TrueNorth is also making use of an evaluation board. But if we were to make everything into an ASIC, can go as low as 50 milliwatts or maybe 100 milliwatts. I'm being too optimistic, maybe 100 milliwatts, the whole system, right? Imagine 100 milliwatts for the whole system. Sometimes your RGB cameras itself can consume 100 milliwatts. Right? Here the vision sensor, the ASIC plus TrueNorth, everything, end-to-end pipeline, just 100 milliwatts. So basically you can plug in the system to a remote location and leave it running for months on end. So it's very, very useful for remote surveillance. Okay, and then something interesting is how does this system in general perform? How does this dataset in general perform for other deep neural networks? Like we examined for tracking, we made use of Siam mask and we compared that output. Now people will also ask, okay, now you have TrueNorth. How is your TrueNorth performance compared to something else? So this is another question they will ask. So here we made use of several models. One is LeNet. LeNet is like the very simple 5-layer network that was proposed way back in 2011, 2012, right? And we compared that to several other variants of it. We don't have to go into too much details, but I can also show you how in detail later on, how a normal convolution is different to a separable convolution and so on. But let me jump into the results, right? That's more interesting. So we have different CNN architectures. You train on ground truth and test on ground truth. Train on RP, test on RP. Train on RP and test on RP, different RPs, right? HIST RP, CCL RP. So the base model is already giving you about 86% accuracy, right?
That's more than human.
I would say, I would think the human is much better. Yeah.
Well, I used to have students to count the buses and trucks. They will be, playing in mobile phone and classify bus as truck and truck as bus. And then says, sorry sir, 200 vehicles missing. They are all bus actually. This guy was talking to me. So I was just counting it as these things happen. So when you say 80%, I am amazed. Wow, that is more than enough to make a decision of traffic control or even accident management or anything.
But this is in the data set, right? I mean, this is in software now.
Software, yeah, I know.
But the actual deployment is about maybe 70-ish.
So that's still excellent. Actually, still very good, very good.
And in terms of flops is floating operations per second versus accuracy, right? You can see how these different architectures are different. And sometimes your base model is enough. You don't need to go deeper and deeper to get higher accuracy. Your baseline model, base separable convolution, can actually give you about 80% accuracy. Again, that's the takeaway that I want to say. You don't always have to go for very complex models to give you a high accuracy. Sometimes mixed architecture and even clever ideas like separable convolutions can give you much higher accuracy. And that's what this neuromorphic field is all about, optimizing for accuracy, optimizing for resources, and making everything into a practical system. In fact, you take a look at each of my slides, it has International Center for Neuromorphic Systems. Like we always have a problem to tackle, a system to develop. We don't just do blue sky research and say, okay, that's done and dusted. No one is going to use it for the next 10 years. We think in terms of systems to build and a core problem to solve. And then another thing that people will ask is, hey, how is your system performing when there is rain, right? So this is a rainy-ish scenario recorded in Singapore. You probably cannot see the rain, but I can see it if I look.
Yes, it is visible. The wetness is there.
Wetness is there, and we are actually recording with the TVS. So we now want to evaluate how this system performs when there is rain. Right? That's the motivation behind this.
Excellent.
Okay, so now there's a big problem, right? Okay, you have recorded using, you have recorded data when there is rain. How do you record data of the same objects when there is no rain? Right? That's the scenario that you're trying to address. But that's almost impossible unless we can now maybe have the same set of cars and same set of bikes go when there is no rain. That's impossible. That's a highly unlikely scenario. So we have to come up with ways to evaluate this particular study. So if you take a look at this area, I will play the video again. You will see that the effect of the rain is not that much. The rain streaks are there in the top and in the bottom mostly. And you can see this RPs, region proposals, appearing and disappearing due to these rain streaks. So if we can define a region of interest for the data and say, remove all the events outside this region of interest, we will treat that data as without rain and the raw data as with rain. Right? So that's the closest trick that we can do to evaluate the system's performance of the same objects being tracked with and without rain. So you can see the strikes, the rain streaks appear in the left video, but in the right video, not so much. It's just like noise, right? And we can do noise filtering to remove it. So this is the system performance, very close between so-called sunny. It's not exactly sunny, okay? We did this trick. Sunny is this performance where we remove this region of, we use this region of interest to remove the events outside of it, because we know that's the road and that's where the objects are. So it's very close. So I would say that overall, our system does not have much effect, because event cameras in general they respond to changes, right? So rain streaks, probably they may not appear until it's like very heavy rain and you can't see anything. And in that case, even event cameras cannot see anything, just like our vision, right? Sometimes when there is fog, we cannot see anything. So even cameras cannot see anything. So it's a limitation for both the event camera and the normal sensor. But our cameras tend to perform better in these scenarios. That's what I would like to emphasize. Summary and discussion. So I've already reached the end of my presentation. You are already thinking, oh, this guy maybe is having 100 more slides and he will go for another hour.
No.
But we have reached the end of the presentation.
No worries, please.
So, what have I presented to you today? So we went through the whole pipeline, right? From data collection to how to annotate, how to automate that annotation, and then how to design the tracker in software first, and how to port that to FPGA, how to optimize that for FPGA. So when you port something to FPGA, you also have to make sure that the software version and the FPGA version is correct. Sometimes they are not, because there are contextualization errors in the FPGA that software doesn't account for. So then we also train true north. Then we have to think about how to deploy the system using the tracker out, not just blindly making use of ground truth annotation and say, okay, let's pump it to true north and see what the performance is. Then we were able to evaluate different scenarios, other DNNs in software setting, not exactly in hardware setting. In software setting, what is the flops versus memory trade-offs? What is the flops versus accuracy trade-offs? How does it perform in training? So these are the different things that we evaluated.
Madam Swarnamukhi, madam, you want to ask something?
Yes, sir.
Please
yes,
do.
Sir.
Please proceed. Thank you.
Thank you, sir. Mr. Bharath, we are really fortunate to listen to your talk. First of all, thank you that I've learned something very new, and I can start, working on this. My question to you is like, I'm basically a computer science student who is doing the research right now. My application is ITS. So I have worked on image processing, and I am good at CNN. So I basically work with convolutional neural networks. So I could relate, something when I, first, listen to your talk, this neuromorphic system. My question is like, say, this TensorFlow, we use it for, for TensorFlow framework, or PyTorch, we use it to work with CNN and with image data set. So if I have to start my learning in this neuromorphic with this vision data set, is there any sources that are available online that I can start my self study, like I can do the study on my own? Is there anything like that, a data set or something that is available? Any sources?
That's a very good question, and I'd like to point you to a resource that is being maintained by INI Zurich. Just quickly bring that up for you and put it in the chat. This is a very wonderful GitHub page that they are maintaining for all the event-based vision resources, right? Whatever data sets exist, whatever papers exist under different topics. So that's a very good place to start, and I'm looking for the chat option.
Oh, here I think maybe you can directly show the site so that I can take a screenshot, because the chat depending upon MS Teams, some of them couldn't receive any chat here. So if possible, just
sure, I can just give you that.
Okay.
Website.
Or you can later. So
if you just Google for event-based vision resources, you will end up with. Come again?
Sorry. Please proceed.
Hi, Swarnam. Thanks for your.
You should have noted all that.
Thank you, sir. Yeah, thank you very much.
I think that's a good question to start with. So there is this page maintained by different people in the neuromorphic community, and they have a table of contents for pretty much everything that you want. They even have a course on event-based robotic vision, a project course that is being now developed at TU Berlin. So I suggest you just Google event-based vision resources. And I'm most likely, I mean, I'm just going to do it now in front of you. Okay, I just do event-based vision resources and I end up, the first thing, it's a good GitHub page. It's a GitHub page which will tell you what this field is about, who are the main players. For example, let's take a look at the people in an organization, right? People in an organization, we are here, Western Sydney University, International Center for Neuromorphic Systems. And previously, Synapse, right? Synapse was also there, Singapore. So you can see that it's a very small community to start with, but now I can see a lot of computer vision researchers are turning their attention to neuromorphic vision. So there's a lot of papers being published in the last 2 years, especially. So take a look at this page. I think it has all the information that you need. And it's being updated like every now and then. If a new paper gets released by our group or another group, it gets updated.
Thank you, Mr. Bharath. Thank you.
I'll be more than happy to be in touch with you if you need some resources. We can even collaborate with students. That's the whole point of having this type of session, right? We have to expand beyond our own circle. So if we see common ground, then we can always collaborate with students, have a mini project, see how it goes, and then we can keep building from there. So
thank you very much.
Feel free to contact me.
Yeah, thank you. Thanks for that.
Absolutely, absolutely. Because yesterday I mentioned IT's business is $50 billion. So our participants will slowly know where that 50 billion is, distributed. You can imagine when they all know about connected vehicle, they all know about basically about how sensors are working and all. But to put that in the perspective and show the challenges there, that's where I think a lot of thinking I would have personally, and especially the comparison of results there. We will. Is there? It seems like somebody's raising their hand.
Yeah, somebody did.
A question, please. Yeah.
Yeah. Professor
Yes.
Bharath?
Yeah.
Am I audible, sir?
Yes,
Prasad, sir. Yes, sir. You are audible. Please continue.
Sir, with respect to the budding civil engineers and transportation engineers,
Yes.
what will be their future? You have told that you have started some master courses in your university. So can we know how about their future chances, whether it's in research or in job opportunities, or how it will be? Can you briefly enlighten us about that?
Yeah, that's actually a very good
Sir, one
question.
second. Yes, sir.
And in general, right, I would go beyond just civil engineering. Any discipline that you take, if you want to actually contribute and move towards innovation, you now have to do interdisciplinary work.
Right, sir. Right. Agree with you, sir.
So, for example, I was thinking.
Sir, 1 second. Prasad sir has 24 years experience as an associate professor, and he is asking this humble question. All other participants should learn from him how he could have been simply quietly watching what you youngsters are doing. He comes forward and asks this question. Thank you, sir. Thank you
very much, sir. Thank you very much, sir.
Thank you, sir.
So I'm just building on that.
Dr. Bharath's answer was multidisciplinary thing. That's the way to go, sir. That I totally agree. I am sure you will also agree, sir. Because we are like islands. Morning you could have seen how many applications Madam said, but they are not actually originated from civil engineering. They originated from computer science. So it's kind of like islands. If we all put together and at the final stage, what we expect transportations would be safe, fast, efficient, fuel-wise saving. That's it. The one bottom line is always that's the thing. Any other questions, my dear friends? So you have Nishta. Am I pronouncing your name, Srivatsava?
Yes, sir. Yes, sir.
Oh, please. Sorry, ma'am. Yes, ma'am. Please continue.
Yes, sir. So, hi, Bharath and Dr. Chandrasekhan. I really feel, first of all, very much honored how yesterday's session was started off by Chandrasekhan sir. And I am from computer field. So, sir, my question to Bharath is, I am currently a PhD student and working on ITS along with the spatial temporal domain. So, is it a wise decision to collaborate spatial temporal along with ITS?
Please say yes.
Well, any sensor that you take, it has to deal with spatio-temporal information. Even the normal RGB cameras, they do deal with spatio-temporal information, but just in a different way, right? They're aggregating, they're waiting for photons to arrive, and then they are integrating those photons and then giving you an image at that time instant. So neuromorphic vision sensors are just another way of sensing, and in that way, even LiDAR, right? LiDAR is also, looking at spatio-temporal information to get depth maps.
Autonomous vehicles, yes.
Yeah. So I would say that it's true for most sensing paradigm, unless you are living in very fast worlds. When I'm talking about fast worlds, I mean, if you think in terms of biology, right? There are applications where event-based sensors have been used to track cells, and you don't need that much spatial temporal resolution, right? You just need the spatial resolution there. That's more important than the temporal resolution, that aspect. But when you come to any practical application, you need to have both these things, right? What would you think?
Yeah, yes,
yeah. Especially, I think. Yes. Sorry, please continue. I was about to say that spatio-temporal thing, especially for pedestrians, we often think transportation means always vehicles or cargo. Millions and millions of pedestrians are crossing the road, and you know how much hectic it is to cross a 6-lane road when there is no crossing there, right? So it seems like most of the accidents are happening because of that gap acceptance problem, right? So what you are saying as ITS is like I mentioned, it's like a broad spectrum of inclusion of these technologies. So I think with further talking with Dr. Bharath, I think Ms. Srivastava, you may be able to figure out even focused some success there. I'm pretty sure. Thank you. Thank you for it.
Sir,
feel free to pop me an email anytime.
Yes, please.
Sure, sir. Sir, one last question I have.
Yes.
Sure.
Sir, do you have a similar kind of link which you had shared earlier for event-based vision resources?
Similar?
Just before like 5 minutes, you had shared one link, right, sir?
Links
for event-based vision resources.
Yeah.
Yeah. So, do we have any GitHub link wherein data set is present, especially with respect to spatial?
You can actually look at that resource, and it also provides you with links to data sets.
Okay, yeah, that's to play with the data set. Okay, good.
That link also has the data sets links.
Yes, I've seen that. Data sets are there, but this is with respect to the vision resources. So I'm looking forward, like the basics, if I want spatial temporal and certain, basically spatial temporal, when we talk about spatial temporal, so whatever papers I've read, in those papers, ANN methods are used, artificial neural network. So I was looking forward to some link which you could share with us.
Maybe we can talk about this offline. You can send me an email. I think that's better.
Sure, sir. Thank you, sir.
Very glad. Miss Dvaita, you would like to ask something? Nishta, thank you. Miss Dvaita, it seems like you want to ask something.
Basically, I'm from transportation background, sir. So
yes.
The question may be like a bit silly, or I don't know, like how you people will take. But I have something in my mind, so that I want to ask it. Since I was going through the presentation also, so I was thinking like how this PIV theory can affect with this sensors. Can it be related to this PIV theory so that accident rates can be reduced like that?
Yeah. Dr. Bharath, I would explain what she is asking. The PIEV, capital PIEV, is a famous traffic theory. Perception, I think intelligence, correct me if I am wrong, Dvaita.
Yes.
Emotion, volition. Perception. Next one is PIEV, perception. Intellectual thing. So it is like something like how we calculate the braking distance. We see first and we don't know what it is, and our intelligence second step says that whoa, that is a person crossing, and our emotion says okay whether we want to kill him or we want to protect him. So then the E's come. The last volition comes. The volition. We make a decision. We finally want to brake. I mean, press the brake and save that person. This is called PIEV theory. Fantastic question, Dvaita, because
very good question.
Dr. Bharath, whether it is perception or intelligence or emotion or taking action, where our technology, the one you are recommending, will fit the most, Dr. Bharath?
Sure. So if you take a look at most of the data that I showed you today, it was from a static sensor point of view.
Okay.
Right? So when the sensor is mounted on a car, like how a human is riding a car, the data that you will be seeing will be much different from a neuromorphic vision sensor, because now you will be seeing everything, right? Because you can see all the gradient changes. You can see everything. There'll be a lot of clutter. So I think your PIEV theory is very relevant to making decisions, much like how a driver would make decisions. But that should be from an ego motion perspective, right? When the sensor itself is moving. For all the things that I showed you today, it's from a static sensor point of view.
Fantastic.
So I don't think that theory is so much applicable, but when you mount the camera on a car, definitely yes.
Fantastic, Dr. Bharath. You see, this is the beauty and this is the magic of asking questions. You see, when you ask that question, everybody, Raghavendra, Rameshwar, Sanjay, Swarnamukhi, Prasad sir, Nishta, Srivastava, and Dvaita, you see, the last question, suddenly we come to realize that that's for the static and dynamic. Two things now are in place where this can be more applicable. There are millions of applications for static thing, because every signal instead of loop detectors can have the camera what Dr. Bharath has. It can point towards the vehicle and do the decision making there. So I think he mentioned that it's not directly applicable now. Good question, guys. Good question. Any Rameshwar, you want to ask something?
Yes, sir. I want to ask that, sir, we can see that through this type of camera, the objects are we can say that it's not showing clearly. It's showing like a negatives, photo negatives, right? Then what are the advantages of this type of tracking system if we capture with if we compare with the normal tracking camera? Then what will be the more advantages of this type of
camera? Advantages.
And yes, please proceed. You mentioned already, but please continue. Yeah.
I think it's a slide that I didn't have, but I think it's a good question, because there are typically 4 advantages that you will have when you're using a neuromorphic vision sensor in place of a conventional sensor. Number 1, you can respond to things with low latency, because these events are being communicated to you in the order of microseconds. So your latency now is lower compared to using a traditional vision sensor. Number 2, you will be consuming low power, right? That's what I've been ranting for the last 2 hours. Low power, low power, low power, right?
Yes.
And the third thing is you will have high dynamic range compared to a normal vision sensor. I liked your analogy to a negative, but you have to understand that the principle of operations of these cameras are encoded now the information is encoded in the time domain, more so in the time domain rather than in the XY domain. So there have been works which make use of an event stream output to actually reconstruct the intensity, and they are able to do it. So the information is not lost. It's still there. All right. So it's just the way you use it. If you want, you can reconstruct intensity and still, make use of traditional methods, but that will be counterintuitive. You might as well make use of a traditional sensor to start with.
That's right.
Yeah. Right. So the fourth thing that we always tout is high temporal resolution. It's connected to low latency, right? So these are the four main ideas where if you think this sensor is going to trump a conventional sensor, you can employ that.
Thank you, sir. Thank you.
Yes, Ramesh. Ramesh, Dr. Bharath said very nicely. Because of we are not here to find number plate or the person who is maybe in phone. That's not the purpose. We just want to know, is there a vehicle there? What kind of vehicle? That is enough. For example, from a loop detector, right? We don't even know what is there. It simply says there is a vehicle. Do you go there and check? There is no even negative or positive or even nothing there. It just tells us some metal is standing there. Yesterday I told you, even if you take a big plate and go, we have tested that. You go up above a loop detector, it will say, "Ting, yeah, there is a vehicle coming," but it won't know whether it is bus or car or anything. If you pull a long metal like 10 meter, it will say bus. So our ITS guy, as ITS, we want to know some kind of information about the vehicle there. We can make other decisions, but we want that to be low power, low memory, latency. He mentioned latency. In cricket terms, if the Dhoni is so famous because of that extremely fast response. He's not saying, okay, there is a ball coming. You know what? Do you want me to catch? No, there is no such thing going on in his mind. It's like the reaction time, they normally put it on screen, 0.4 seconds, 0.5 seconds, right? So sir is talking about milliseconds, so that will be great. I think I was just pulling more on what Dr. Bharath was saying in terms of our own traffic terminology. Guys, anybody wants to ask any more questions? Is it like Ms. Sonamurthy, your hand rising?
I think it was an
old one. It seems like somebody is talking.
Yes, sir. Kannadasan, sir.
Kannadasan, sir? Yes, Kannadasan, sir. Please ask. Yeah.
Yes, sir. We can use UAV camera for this kind of instead of digital cameras. We can go for unmanned aerial vehicle for studying some of stretch like signalized, unsignalized.
I mean, I'd like to show something here. I'd like to stop presenting, and in fact, this is just one project that we did using this neuromorphic vision sensor. The other project was exclusively focusing on a neuromorphic vision sensor on a UAV.
I see. So they go there and stand there and take the pictures. It's not like
not exactly. I mean, there's no picture here. I mean, it's just sensing temporal changes.
Yeah,
I know it's a bit difficult for people who are adapted to image processing technology. So I'll just quickly show you a video where this kind of technology, when applied to UAVs, is.
We are pushing the last question.
All right. Are you able to see my screen? Yeah.
Yes. Research topics, event-based division.
So I see this YouTube video.
Wow. Okay.
So that's a downward-looking event camera moving around our lab, and now we are actually doing everything on board the FPGA. Right. So the output that you're seeing in class is this thumper object. So you can also detect the thumper over there. And then when you move around to another object, then you will see, okay, there's a lot of background, and then there's this landing platform. And then when you move around again, you will see a lot of background because now you're hovering over the landing platform.
Fantastic.
Right. So this is again, this is another stream of research that we did. Here you switch off the lights, you can still see because it's just changing the temporal difference. Absolute light intensity doesn't matter.
Fantastic.
Right? So it's still sensing there's a landing platform beneath it. All right. So once you move out, then okay, you do a full round, you will see thumper, you will see background, and when you move across that object, you'll see landing platform. Okay, you'll see a lot of background. Okay, then when you move across that UAV, you see UAV a bit.
Wow.
And then you see the thumper again, and then this can go on. So this is a completely online system.
Fantastic.
That is a different stream of research compared to what I presented today. So you can take a look at our page, nusneuromorphic.github.io.
I see.
It has all the other research that we did previously.
Excellent. Thank you so much. Because the Kannadasan sir asked, and we could able to know something related and still, new and
One
yes.
more question, sir.
Yes, please.
Sir, you are explaining about CNN. What about RNN in case of these studies?
Okay, so RNNs can be useful when you are trying to make use of the event camera data natively, right? Here we talked about CNNs because this is a hybrid neuromorphic framework. It doesn't make use of the temporal resolution as such. We already aggregate the information into a frame and then feed it to a CNN, right? But imagine you are feeding the native information of the camera to an RNN. It can actually make use of the temporal spikes.
Yes, sir. You
So it depends on the application.
You studied with one stretch in homogeneous traffic condition, right?
Yeah, that's a good.
What exactly you mean by homogeneous?
That's where I come in.
But in case of coming to our Indian
wait a second, sir.
Kannadasan
sir, wait. Yes, when he says that, I'm not sure. That's where I come in.
Okay.
Dr. We have transport. We have two kinds of traffic system. One is lane based, which is in advanced countries we have a lane. They all form a queue, and of course the other part, no lanes. Even though lane marking, I am the king. I can go. I am the queen. I can go anywhere I want. As long as I find a gap, I will go and stand there. So that is called heterogeneous traffic. The first one is called homogeneous traffic. Okay, in fact, I was also about to ask. So Kannadasan sir, he asked my question actually, because the system you showed, it seems like it requires a disciplined traffic condition to be applied or something like. Is it like something like that?
I would say yes to that question, but okay. So for example, if you have the training data that is that is belonging to a different system, then definitely you can deploy it there. But it depends on the training data that you have.
Fantastic. Yeah, I think Kannadasan sir, did you listen to what he said? Since it's NN neural, anything related to neural is all about training. Just we had some little kids in our terrace yesterday. The kid is learning about pasting something, and we were just observing how he is learning to pick it up and place it. It falls like 100 times. It's just doing it again and again and again and again. Like it is amazing to see, watch kids how they learn. Of course, until to certain point, So then they start crying. That's a different story. Okay. So is there any other question, guys? I think we are holding Dr. Bharath for a long time, and I thank Dr. Bharath so much with utmost gratitude. Dr. Bharath, thank you so much. Thank you. We will all close the session. Thank you so much. Take care. Take care.
Thank you very much, Chandra, for this opportunity, and I'm happy to always communicate ideas. And I really enjoyed this session, and I hope you did too.
Definitely. Thank you very much. Take care. Thank you. I will get back to you. Thank you.
Thank you.
Thank you very much.
Thank you, sir.